You. Welcome back, you. We are going to start part 3 of the review for Unit 5, the definite integral for the AP Calculus AB course. This is just review. We are not doing day 1 for Unit 5, day 2 for Unit 5, day 3 for Unit 5. We are reviewing the whole unit. All right, if you want to do day 1, day 2, day 3, those are available as well. But the review is the meat and taters. I say that every time. And you should have seen this stuff already. Maybe you've forgotten it, or maybe you just need a review of it. We last left off, we ended our part 2 video with U substitution. So let's pick up with, I think, some sort of fundamental theorem, something. Let's check it out. And here we are. The fundamental theorem of calculus tells us, learn math. Okay? That, and this I like to tell to my kids, this is more of a no-brainer, all right? This is kind of a no-brainer, meaning if I take the derivative, okay? If I take the derivative of an integral, okay, I should end up with my original equation, meaning, and let me give you an example, all right? Multiplication and addition, okay, no, they kind of go together. Multiplication and division are opposites, right? Addition and subtraction are opposites. If I'm solving for something, I need to use opposite math, correct? If I have 3x plus 7 equals 16, right? I know that first I subtract 7 because subtraction is the opposite of addition. I have 3x equals 9. And to get rid of the 3, I divide because I'm currently multiplying, so I use the opposite math, right? So well, it's 3, Visca, that's your answer, okay? But ultimately, integrals and derivatives we can kind of view as opposite math. If I have an equation, let's call it with a variable t here, okay? 3t squared dt. I want to take the integration, that's why I put this dummy variable. All right, I have some constant down here, I don't know, 5. And I have an x up here, okay? If I'm integrating this, but I want to take the derivative of the integration, okay, these things cancel out, okay? And whatever variable is up here, okay, when I cancel out my integration, that also cancels out the dummy. And whatever variable was here was an x, it just becomes that, all right? It just becomes that. So, chain rule. Remember our friend chain rule? Oh, the chain rule. Okay, I don't know why that keeps on disappearing. I guess it's just going to keep on disappearing. It's weird. Sometimes it does, sometimes it doesn't. But the chain rule, this was an x. So we are always multiplying by the derivative of whatever this upper thing is. The derivative of x is 1. Okay, so really anything times 1 is itself. So as long as we have an x in our upper bound and some constant in our lower bound, this constant could have been 5, 12, pi, Euclid's number, e. It could have been anything. Okay, as long as there is a constant in the bottom for the lower bound and that variable in the top for the upper bound, I just put that variable in for my t. And that's it. I mean, it's really quite that simple. All right, so let's take a look at an example right here. All right, I'm taking the derivative of an integral, so I know they're going to cancel, okay? I know this variable is going to go in for this t, so the derivative cancels with the integration. My dummy variable goes with the integration. My bottom is a constant, okay? My bottom is a constant, so this is cool to do, and this top variable is going to go in for t, and that's it. So it's 1 over 1 plus x squared times the derivative of x, which is 1. Okay, we don't have to do that because anything times 1 is itself. Okay, very simple. But here come the questions. Okay, and when I taught this in the unit, in the daily unit, not the review unit, but for unit 5, day 1, 2, whatever, here are the questions. What if the upper bound is the constant? Okay, what if my x is on the bottom, my 5's on the top? Well, we got to remember our rules for integration. I'm still going to take the derivative. Okay, I can flip my bounds, and if I flip the bounds, I have to negate my integration. Okay, so it's still 3t sine of t dt, okay, which equals, all right? Again, I now have, since I flipped them, a constant on the bottom, my variable on the top. This variable is going to substitute in for my t's because my derivative is going to cancel my integration, which cancels a dummy variable, and I have 3x times the sine of x. Don't forget, this negative is like multiplying by a -1. There you go. That's your answer. That's your answer. Okay, but you might say, but when we did integrations, wasn't there like plus a c? That's if there were no bounds. There are bounds here. Besides, we're taking the derivative of whatever the integration is. So the constant will go away, right? The derivative of a constant is 0 anyway. All right, so if the upper bound is a constant, we just flip and negate. Pretty simple. But what happens, what happens if the derivative variable, okay, and the upper limit do not match? What does that mean? Derivative variable and this don't match. See, this is an x on the bottom here. This is not an x, it's x squared. Here they matched. X and x, I flipped it, right? Here they matched, an x and then x. Now we have an x and an x squared. Hint, oh, here it is again. Oh, you guys probably can't hear it. It's my boy, Jibs. Here we go. Here we go. Do your chain hang low? Does it bow to the floor? Does it shine in the light? Is it platinum? Is it gold? Oh, I'm sure you probably can't hear it. It's probably very faint, but oh, does it chain? Okay, I got to close it down now. I'll just stay off math the whole time, and you won't appreciate it. Anyways, we got to do the chain rule. I've been telling you this, okay? So I am taking the derivative of integration, which will cancel. And this goes into place here. So it's cosine of x squared times the derivative of whatever this is. The derivative of x squared is 2x, so times 2x. But we're good at math, and we know that any constant or variable that is not being trigged, I'll call that trigged, that is not the input to our trig function. Okay, anything that's outside of it should go up front. So I would write it 2x cosine of x squared. Put the parentheses around that x squared because you were taking the cosine of not just x. You're not squaring, don't leave it like this, please. Because some might say, well, you're taking the cosine of x, then squaring it? Or are you really taking the cosine of x squared? Never leave it up to your math teacher to interpret that because they don't know as much as you do. There, I said it. Unless I'm your math teacher, which I know everything about anything. But just don't ask my wife. She'll say I know nothing about everything. All right, so here we go. 2x cosine of x squared. What's the one difference? We always multiply by the derivative of that, 2x. We did the same thing here. We multiplied by the derivative of x. It happened to be 1, so we didn't really write it. Okay, we did the same thing here. We multiplied by the derivative of x, which happens to be 1, but, you know, we don't write it. So we're always doing the chain rule. Just sometimes when it's 1, we don't waste our time writing it. Okay? And then, boom! Visca, I trusted you. I trusted you, man. And I'm so sorry. But let me make it up to you. What if there is no constant? What if I'm taking the derivative of an integration and there is no constant? All right? Here we go. You ready? We can split this up into 2 integrations. Okay? What do I mean here? Let me get my coffee because this is going to take a second. good stuff, that French vanilla creamer, but you got to get the sugar-free stuff. The sugar will kill you. Anyways, I'm taking the derivative of this integral, but I'm going to break this up. I'm going to take the derivative of this whole thing. Well, one of my integrations, I'm going to have my x squared on top. Okay, I'm not going to put the bottom here yet. Okay, I'm going to leave this blank for right now. I will write it in a second. Of 1 over 2 plus e to the t dt, okay, plus the integration. Okay, now you see how I kept the top one up top? I'm going to keep this bottom one down low, 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 low. Apple bottom jeans. Okay, anyways. And for this one, I'm going to leave the top because I don't know what to put yet. I mean, I do. I'm going to tell you in a second. Of 1 over 2 plus e to the t dt. Okay? Now, here's the poo-poo. We're just going to put a 0 here and here. So here's the question that I always get. Well, Visca, and you don't have to write this down. This is an explanation. And I always get this question. Let's say x squared is here on the number line. Okay? Here's 0. Because whenever I square a value, it'll be positive. Right? Right. Okay, well, how do I know 2x is here? How do I know x is a negative number? Okay, if x was negative, this would be on the left of 0, and this would be on the right. But what if x was 1? If x was 1, this wouldn't be here. This would be on this side. Okay, well, if that's the case, we won't use 0. You can use, I don't know, oh my God, if x was 3, let's call it. Because if x was 1, those would switch. But anyways, if x was 3, what if x was 3? Okay, this would be 6. This would be 9. I can't use 0. Okay, well, 7 would be our constant. Does it matter what our constant is? It does not, because the constant goes bye-bye. Look at, boing, over here. Did the 0 come into play at all? No. Did this 5 come into play at all? No. It had no effect on it. In fact, did this 0 come into play at all? No. The rule here is, as long as this is a variable and a is any constant, it could be anything. 0, it could be 7. I believe they said pi, Euclid's number. It could be anything. So it doesn't matter what I put here. Okay, now that's what just happened. Let's go back. Doesn't matter what I put here. So by default, I put 0, whether it's between them or not, because really, that's going to represent any constant. And any constant, it won't have an effect. All right, do you understand what I'm saying? All right, now, let's go. Now we're going to do this using the same rules. This one I could do, that's good, but this one here, my variable needs to be on top. So guess what? I need to switch my upper and lower bound. And when I do that, this becomes negative, doesn't it? So instead of rewriting this whole thing, I'm going to put my 2x up here, lazy. I'm going to put my 0 down here. And now that becomes a negative. Because remember, when we switched our 5 and our x, we had to negate, okay? So now we have to negate it. And we can take the derivative of both of these integrals. So guess what? My derivative cancels with my integration and cancels with my integration. This variable goes in for my t. This variable goes in for my t. So let's rewrite these. This one first. 1 over 2e to the x squared times the derivative of x squared. Chain rule. Does your chain hang low? Does it bobble to the floor? Does it shine in the light? Is it platinum? Is it gold? Okay, so now minus. Wow, EL education. Who cares? Let's cut that out. Boom, done. Now 1 over 2 plus e. It's not to the x squared, it's to the 2x. Times the derivative of 2x, which is just 2. So because we're good at math and we want to show our teachers that we are impressive, we're just going to combine these. We're going to combine this and combine this, and we're not going to combine anything else. So I got 2x over. Where'd my plus sign go? Right there. Weird. 2 plus e to the x squared minus 2 over 2 plus e to the 2x. That is an absolute perfect response. I almost want to say I love you for how much math you know. I respect you for what you do and because you're here with me trying to be better at this stuff. All right? Good deal. Good deal. Not too bad. Let's see how we're doing with time. 15:30. This next is called part 2 of the fundamental theorem of calculus. It's also known as the integral evaluation theorem. This is so crucial, okay, to understand just the basic concept because it always seems to appear at least once on the final. Okay, and it might only appear once. And when I explain it in full detail, you'll say, oh, well, that's like kind of common sense. And it is, but we really don't think of using it because it's such common sense to solve things. But we do. This is saying, if I integrate something, little f of x, well, the integration of this function we'll call capital F. Okay? Don't I need to take that function and I want it from b and then subtract it from a? That's all I'm doing here. If that doesn't make sense, I will give you an example, and you'll see what I'm talking about, okay? Everybody always gets it with examples. So, blue. No, purple. Okay, let's integrate from 2 to 6. All right, let's make it simple, just 2x plus 4 dx. Okay, my function is this right here. When I integrate it, so here's what I want to write off to the side here. F of x is 2x plus 4, okay? So when I integrate this, I'm going to get x squared plus 4x, okay? That's capital F of x. So when you see a capital F, they're talking about the function after you integrate it, okay? That's x squared plus 4x, all right? But because I have bounds, don't I want this from 6 to 2? And in order to solve that, don't I take 6 and I plug it in? So I take 6 squared plus 4 times 6. And I take that value and I subtract throwing a 2 in there. So it is 2 squared plus 4 times 2. So this should be understandable from right now, okay? You should understand what I just did in purple down here below. So let me relate what we're doing here, okay? This equation, okay, this whole integration from b to a, from 6 to 2, okay, is equal to f of b minus f of a. So when I look down here, plugging a 6 into this equation is like saying f of 6. I'm plugging 6 in. That's what that equals to. Minus, okay, that's like taking our f equation and plugging in 2. Okay, so this thing is this thing. So we're just, which in effect is just putting in those numbers. So yes, this is equal to this. So yeah, Visca, that's just common sense. It's just math people just do things. Math people just do things and it's crazy. And I don't understand it. Like, why would we have to understand this if we can do this? Because, oh, you will get a question somewhere along the line. Let me try to make one up here. Okay, I'm going to integrate this from 1 to 9. The integration of f of x, they'll tell you dx is, let's call it 11. Okay, and it'll be a word problem. They'll say the integration of f of x from the bounds 1 to 9 or whatever is 11. Okay, then they'll also give you, they'll say capital F of 9 is 3. Find f of 1. And without, initially you're going to say, I don't know what the equation is. How can I integrate this if I don't know? Because this right here, which is 11, equals f of 9 minus f of 3, okay? And f of 9 is 3 minus, well, now what's f of 3? Well, it equals 11, right? 3 minus a negative 8 is 11. So f of 3 has to be negative 8. Or excuse me, yeah, I'll be okay. The 3 was here. F of 1. I'm so sorry. Okay, because here are my bounds. I was just thinking about this thing. I threw that. F of 1. So f of 1 is negative 8. So you don't even have to know the equation. If you have 2 of these 3 pieces of information, you can do this. Okay? And a lot of the times what they'll do on the answer key, let me go leave it like that. Yep, that was my eraser. Okay, so they give you this, and you need to find f of 1, right? Which is this right here. Okay, they're like, what is f of 1 if f of 9 is 3? What they'll do is they will subtract f of 9 from both sides, right? So now I have the integration from 9 to 1 of f of x dx minus f of 9 equals negative f of 1. Okay? So this was 11 minus 3 equals the negation of f of 1. So we say 8 equals the negation of f of 1. And if I negate both sides, f of 1 is negative 8. Okay? So they'll give you a scenario like that. It might not be written the way I explained it, but they'll expect you to know that. It's just a basic thing to understand. Okay? And that was cool. We did good. The trapezoid rule. This one pops up on the final as well a lot. Okay? The trapezoid rule tells us, okay, this is just like LRAM, RRAM, and MRAM in the way that it looks, in the way you deal with it, except instead of using rectangles, because these RAMs are the rectangular approximation method, we're not using rectangles, we're using trapezoids, okay, for the area under the curve. And it goes as follows. The H, which like if I were to graph something, okay, and I were to have 4, well, in this case, they're not rectangles anymore, they're trapezoids, okay? I do this, I go up, and I do this, and like that. The H is the width of each one. It should be the same, right? Should be the same. Maybe this one goes up to here, it comes up like that, whatever. This one goes up to here, it comes up like that. All right? So the H is just the width of your trapezoid, or in this case, the height. Because if I took this trapezoid right here, okay? Okay? And I were to take this out and lay it on its side, boom. They call this height because it's the height of the trapezoid. Although, when it comes into our graph here, it is kind of sitting on its height. Wow, that was weird what just happened there. Bam. So, oh, now we can move that back there. Boom. Everything is right in the universe again. So that's where this H comes from. All right? However, instead of just adding up all the Y values, you'll notice one very specific thing. So let's review. This is the width, or in our case, the height. It's always, always, always divided by 2. Remember when we did LRAM and RRAM, it was always our height, which I like to call W for width. And I multiplied it times all of our Y's, right? Adding up all of our Y's, that. And in the one problem, we had up to 4 of them. I'll just put an N here, okay? There's a difference between the RAMs and the trapezoid. I'm always dividing this by 2, always. That never changes. But mister, when I do it, there will always be a 2 on the bottom. Yes. Okay, it is always your height divided by 2. Next, I still add all these things up, but what you'll notice here is the bookends stay the same. Y0, the first Y you use and the last Y you use, I call them the bookends because they smush. Okay, they're bookends there. Stay the same. Every other one in the middle gets doubled. I multiply this Y by 2. I multiply this Y by 2. I multiply this Y by 2. And I could explain that. I mean, I will right now, but if you just understand that the process, the way it's set up, you really don't have to understand this at all, what I'm about to tell you. When I use this trapezoid, okay, we'll call this side A and this side B. And then we got this trapezoid, side C. All right? I need to use A and B for my first trapezoid. We'll call that here. Boom. Then I need to use B, and C for my second trapezoid. Notice I had to use B twice, my second term. This is my first, y sub 0. I only have to use it once. I had to use this, y sub 1, twice. That's why I have to double it. Okay, so now let's go on to the next one. I've got to use C again and D, which means I had to use y2 twice. Boom. And I keep on going. I have to use D and E. Now I've used D twice, which might be this one. But notice there's nothing after E, so I don't have to use E again, do I? So the end, just like the beginning, I only have to use once. Now, if you didn't understand that, that's fine. What you do need to understand is the formula, the setup, if you will. You always take your height divided by 2. Trapezoid, it's a T. You know what also begins with T? 2. It's divided by 2. All right? And you'll notice that there are 2 y values, the first and last, that do not get doubled. And you know what happens to the rest of them? They get multiplied by, guess what? 2. So a T, if you remember T for trapezoid, you'll remember everything. The 2's, okay? You'll remember that T stands for 2, which means I divide my height by 2. There are 2 values that don't get doubled, the first one and the last one, the bookends. And then everything else gets multiplied by 2. Okay, I can't make it any easier for you to memorize, okay? This will get used in the final at some point, all right? Let's advance. Let's move forward. Okay, Simpsons Rule. God, I love the Simpsons. That's great that there's a Simpsons Rule. All right, this is the same thing as LRAM, RRAM, MRAM, or Trapezoid Rule in the manner in which it is set up. It is very similar in S to trapezoid, with the bookends being the same, and you got to take your width or your height and divide it by something. But, oh boy, there it is. All right, here you go. I am always taking my height, in trapezoid divided by 2. My height actually will always, always, always be divided by 3. Always. And just like, I should use a highlighter because I'm writing over these things. That's why I like the highlighter so much. Not so much that it's there, but you're always taking your height and dividing it by 3, or your width. Okay? Now, the bookends stay the same, just like the trapezoid rule. Notice I am not doubling those. Okay? But for Simpson, okay, for the Simpsons rule, you're not multiplying everything in the inside by 2. You're rotating, okay? The first one after your bookend gets 4, then 2, okay, then 4, then 2, then 4, and then it ends where you do nothing. That's the only difference. I am not going to explain that like I did the trapezoid rule, although I could. It has to do with like parabola arcs. It's crazy. Not really, but it's unnecessary for you to understand completely. If you want to look up the basis for Simpsons rule, go ahead. But for the sake of time, I'm not going to explain that. Just like trapezoid, except 3. Okay? You divide it by 3. And instead of everything being doubled inside, the bookends stay the same. Everything inside isn't doubled. It's 4, then 2, then 4, then 2, then 4, then 2. And it repeats that pattern until you get to your end book. Okay, your end bookmark there that does not get doubled. All right? And that's it. All right, so let's take a look. We have a couple more problems to do. And these all revolve around the trapezoid rule, not Simpsons rule, because I think, or I know that 99, I'll call it like 97% of the time, if they ask you to do any sort of calculating using an area under the curve, maybe they say LRAM, RRAM, but between trapezoid and Simpsons rules, they are definitely going to use trapezoid rule more so than Simpsons rule. Where are we at with time here? We are right at the 30-minute mark, okay? In about 30 seconds. That was weird. 30 seconds, 30 minutes. Hey, that's me. But we will have one more video, part 4, and that video will just be the next 3 problems. 1, 4, and 5, okay? And then the rest of this packet is problems for you to work on. Now, it's Christmas time. What do they do for Salvation Army? Ring the bell. That's right. Ring it, like it, comment, do whatever you want. Follow. Hey, I don't think it's weird if I'm walking down the street and there's like 7 people following me. People are like, who are those people? And I'm like, I don't know. I'm like, who are you? I don't even know you. And like, no, you don't. But I like being around you for some reason. They do that sometimes. That happens, honestly. But anyways, like me, follow me, ring the bell, do whatever you want. Leave a comment. I will answer. All right. If I notice a little notification, I mean, I don't live and breathe this social media stuff or this YouTube thing. But if I do see a question or a comment, I will reply if the notification pops up. All right. So I will see you for part 4, in which we will do 3 problems, which don't include the number 3, but include the number 4, because we go to 1, 4, and 5. Weird. All right. See you then. I like your grit, man. You're sticking with it. Keep sticking with it, because you will ace this stuff. Fantastic. See ya. Let me go here now. Oh my God, now I'm over 30 minutes, almost to 31. I got to stop it before it gets to 31. Where's the button?